Welcome to Math 2318. This is section 3.2. We're looking at more details here in this section on determinants. So let's see what's going on here in question 1. We're given the determinant of this 3 by 3 matrix. Let's see, we got 9, minus 9, minus 5, and 2, which was row 1, and now it's row 2. Row 2 is now row 1. So what's going on is we switch two rows. So let's see, if we had a 2 by 2, the determinant is AD minus BC. And now if I switch the two rows, I get BC minus AD, which is minus 1 multiplied by the determinant of the original matrix before I switch the rows. So what's going on here is that switching two rows, I pick up a negative 1 times the determinant of the original matrix. Alright, so in question 2, how are these related? Well, let's see. If you look here at row 1, if I take 3 times that row, so 3 times 1 is 3, 3 times minus 2 is minus 6, and 3 times 3 is 9. So I've essentially multiplied a row by a number. So anytime that you multiply a row by a number, it is that number times the determinant before you did the multiplication. So multiplying a row by 3 multiplies the determinant by that same number. Alright, question 3. Let's see if anything got switched. No, row 3 is still there. But now row 2 seems to be different. I've got a 0 here, so what happened is we multiplied the first row by minus 3, added it to row 2 to generate a new row 2. But by doing that, I have not changed the determinant. It's only if I swap two rows or if I multiply a row by a scalar that I change the determinant. But adding two rows together to make a new row does not change anything. Alright, so let's see. Here in question 4, we're going to reduce this to echelon form. So remember, multiplying a row by something, adding it to another row, is not going to change the determinant. So you use this 1 to make two zeros. Alright, so we did that. Now I'm going to use this 1 to make that a 0. And so armed with that, here is my echelon form matrix. And so now I'm going to calculate the determinant, and I'm going to expand down the first column. So 1, the position here was a plus 1, times this cofactor. And this cofactor is easy to do. It's just 12, and so 1 times 12 is 12. Alright, in question 5. So we are given that the determinant, this 3 by 3 determinant, is 5. So what happened? I multiply 8 by row 3. But by doing that, that means it's 8 times the original determinant. And so I've got 8 times 5 is 40. So remember, multiplying a single row by a constant is that constant times the determinant of the original matrix. All right, what about here in question 6? What's going on? A, B, C, D, E, F, G, H, I. In that case, my determinant is 18. All right, minus is 18. And so now what's going on? I'm going to swap out the 2 rows. And by swapping out the 2 rows, that means I'm going to pick up a minus 1 times the original determinant. In question 7, I want to see if these 3 vectors are linearly independent. Well, the way to do that is to calculate the determinant and see if it's 0 or not. All right, so here's my 3 by 3 determinant. So let's see, I'm trying to pick which row or column is going to be the easiest. I'm going to pick the last column. It's got positives in it. It's got this 0. So the position signs would go plus, minus, plus. So I've got a plus 5, and I cover up the row and column. 6 minus 5 minus 1 and 5. Similarly with the 5, I get nothing from the 0. So I get 5 times 25 plus 5 times 11. And so for a total on the determinant of 180. So the determinant is not 0. So the vectors are linearly independent. And in question 8, we summarize lots of properties of the determinant. First off, the determinant of a product is the product of the individual determinants. So in our case, I know the determinant of A is 4, determinant of B is 7, and so the product is 28. Multiplying a scalar by a matrix is going to be k to the n. What's n? N is the size of matrix A. So k to the n times the determinant of A. And so 5 times A, well, if A is 3 by 3, that's 5 cubed, which is 125 times 4, which is 500. What about the determinant based on A and its transpose? Well, it turns out that by taking the transpose, I get exactly the same determinant as the original. And so for B, whose determinant is 7, the determinant of the transpose is also 7. What about the determinant of an inverse? Well, it's 1 over the determinant of the original matrix. And I know that that's well defined because A inverse only exists if the determinant is not 0. And so in this case, I would get a 1/4. What about the determinant of A cubed? Well, that's the determinant of A times A times A. So I've got a product of 3 determinants. Each of them is 4. So essentially 4 cubed, which is 64.